water, it's great to be fishing. But fog does tend to dim your enthusiasm. Don't despair. Your handy compass works in rain, hail, and yes, even fog. Unless, of course, there is something which throws the compass off. In which case, you might be in for a bit of a surprise. A compass needle is simply a magnet. And an attractive force exists between magnets and iron objects, even at a distance and even through the vacuum of space. It's as if invisible hands pull the magnet and metal together. In this way, magnetism is similar to the forces that charged particles exert on each other. These forces act over a distance in the same mysterious way. During the 17th and 18th centuries, electricity and magnetism developed as separate sciences and were believed to be unrelated. Then, in 1800, Alessandro Volta developed a device that paved the way for a change in this view. His device consisted of copper and silver coins, arranged in a column and separated by pieces of cardboard soaked in salt water. When he attached a conductor to the top and bottom, like this, and brought the two ends together, a spark resulted, indicating that a flow of charge was occurring. Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around a conductor with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately. what happens to the overall shape of the magnetic field if the conductor is bent into a loop? Let's turn the current on again and find out. If we apply the left-hand rule at different points along the conductor, we can map the magnetic field around the loop. Notice that the shape of the field resembles a donut. But if a number of identical loops are added, the resulting figure is called a helix or coil. Looking at the coil in cross-section, we'll represent electrons flowing away from us as X's. And here at the bottom, electrons flowing towards us as dots. Applying the left-hand rule for conductors to each turn of the coil, we can begin to build a picture of the magnetic field around the coil as a whole. Since the distance between the turns of the coil is very small, we might think that the fields would overlap like this. But this is not the case. Magnetic fields do not overlap. Instead, the field of one interacts with the field of the other to produce a combined field like this. If we examine the area between two of the turns, we can see that the two interacting fields effectively cancel each other. This field interaction occurs between each of the turns of the coil, resulting in an overall field which surrounds the turns and resembles a somewhat flattened oval. The same oval pattern is produced at every point around the coil. And it's the merging of all these ovals that forms the magnetic field for the entire coil. Since the field direction of each oval is the same, then in the center of the coil, cancellation does not occur, and that portion of the field is very strong. There is also no cancellation outside the coil, but because the field is spread out, it is much weaker here. The relationship between the direction of electron flow in the conductor and the direction of the field in the center of the coil is given by another left-hand rule, the left-hand rule for coils. This time, the fingers curl in the direction of electron flow, and the thumb points in the direction of the field within the coil, or to the end of the coil that acts as a north pole. The fingers curl with the current, and the thumb points north. If we compare the magnetic field of the coil with the field of a bar magnet, we can see that the shapes are nearly identical. Each has a north and south pole. But an ordinary iron bar has no magnetic poles. What then happens if we insert this bar into a coil with current flowing through it?